We have Vidit Nanda with us, who is working in the area of data analysis, but applying various techniques from topology. And he will be discussing about path signature and topology dynamics and data analysis. So we really welcome Vidit in the John Conway Spirited Seminar Series, and I hope this should not be your last talk, and we can have many more in the upcoming years. So Vidit is currently affiliated in the University of Oxford, and he's working on techniques what he's going to discuss today. Over to you, Vidit.
Thanks so much, Imran, for the invitation. It's lovely to be here. I think this is the first talk I'm giving in Pakistan in any sort of capacity, online or in person. So it's very nice to be here, and good to see so many of you here. So yes, the title is Path Signatures in Topology, Dynamics, and Data Analysis, and I will be telling you about this for the next 50 minutes or so. But first, I wanted to tell you, I have seen John Conway exactly once in my life. The great man himself came from Princeton and gave a lovely talk at Rutgers. We were graduate students at the time, and we were just in awe. I think he was quite old at the time. He had mobility issues, but he still managed to somehow give a spectacular presentation. Lots of energy. It was great. So anyway, so it's lovely to be in a seminar series with his name attached to it. So let's see, the outline of this talk has sort of three different areas. This talk is going to go through three different areas, and I'll try and describe what those are a little bit. So the starting point of the talk will be in algebraic topology. This is my field. This is something I know and love. This is what I do. And so this is where we start the story with the study of objects in algebraic topology, which I'll describe in a bit. But from here, we take a sort of detour to the study of dynamical systems. And this is very much not what I do. It's not my specialty. But we will see some very interesting interfaces between the study of objects in algebraic topology and the study of very different looking objects in dynamical systems. From there, we will go to data analysis, machine learning, things like that. And then once that journey is complete, we return to topology, but from a very different place from where we had started. So that's the journey of this talk: topology to dynamics to data to a different part of algebraic topology. So I'm going to get started with the topology bits. One of the most interesting objects in modern algebraic topology is called the loop space. And you can take any sort of topological space, like imagine the torus over here, for instance. And its loop space is a set of all continuous maps from the circle to that space. So I've drawn over here two different maps from the circle to the torus. And each of those maps now becomes a point in the loop space. It's not, so it's a space of all these maps. So the upper arrow is one point in the loop space of the torus. The lower arrow is another point in the loop space of the torus. If you moved the top one a little bit up, you get a completely different point in the loop space. So it's sort of difficult to describe, but if you think about how many directions would perturb one of these maps, there's no finite bound. So even if X is a nice, in this case, the torus is a nice two-dimensional surface, there's nothing finite dimensional about its loop space. So it's usually a very sort of complicated, very scary, infinite dimensional loop space. The reason it's of interest in homotopy theory is the fact that it's sort of an adjoint to the suspension. So in order to make sense of that, there's an operation in topological spaces called the suspension. Maybe some of you've seen it, maybe you haven't, so let me describe what it is. So if you take the space that just looks like a Y. So the graph with sort of 4 vertices and 3 edges arranged in the shape of a Y, like on the right-hand side. Its suspension is what happens: take a point above, take a point below, and then just drop curtains from the top point to the bottom point. So that's called the suspension. And when I say that the loop space is a homotopic adjoint to the suspension, what I mean is homotopy classes of maps, functions, smooth functions, from Y to the loop space of X correspond bijectively to maps from the suspension of Y to X.
Excuse me,
Yes,
can I have a question?
sure.
Okay, so what do you mean by compact open topology? I am not familiar with this name, maybe some other notation.
No, that's a good question. So it's a topology whose basis is given by pairs of compact sets in the codomain. So a compact open topology is a topology on mapping spaces. So you have an X and a Y, and you're looking at maps from X to Y, and you want to put a topological structure. So this is the natural notion that does that. So you take a basis for this topology is compact set in the codomain whose inverse image is contained in an open set in the domain.
Okay. Thank you very much.
No worries. Okay, so so omega serves as this sort of dual notion. It's almost like it's an adjoint to the suspension operation on topological spaces. And if you've seen any homotopy groups, the ith homotopy group of the loop space is isomorphic to the I plus first homotopy group of X. So even though it's very, very complicated to describe, it's not, like I said, it's not a finite dimensional space. Its homotopy groups are really nicely related to the homotopy groups of X. I mean, so if X was nice and somehow homotopically simple, then its loop space could not be homotopically very complicated, even though as a topological space, it could get quite ugly. And there's a product. So you take 2 points of the loop space and you can smash them together to create a new point of loop space. So one way to do that is to choose a base point. And so all your loops start from that base point and come back. And so the product would be you start from the base point, do loop 1, and then do loop 2, and you realize you have another loop on your hands. So that's the product operation. It's just composition of paths which have a sort of point in common. And although I will not be talking about that in this talk, because it's sort of scary and I don't know that much about it anyway. If you've seen any modern homotopy theory, the study of spectra, I mean, loop spaces are the first thing you see. So it's the ground floor for a very, very tall building. If you're interested in things like this, there's a lovely little book by Frank Adams called Infinite Loop Spaces. It's written in a very friendly style, even though it's dealing with some very scary matters. So I would recommend that book if you care more about loop spaces. Anyway, okay, the things one would want to do is, for example, learn about the homology or cohomology of these loop spaces. And like I said, the infinite dimensionality makes it very hard to use any of the standard tools that you have for computing cohomology. The usual thing you do if you want to compute the homology or cohomology of some space is to put sort of a structure or a simplicial complex or a cell complex on it. And then you get a nice little chain complex from which you can compute homology if you've ever done that before. This is not so feasible when you have an infinite dimensional space. I mean, there's no known cellular models for the loop space of any given X. Okay, well, we can restrict. So when X is a smooth manifold, not the loop space, but X itself, the underlying space with loop space you take, when that's a smooth manifold, you can try to use something we know about as cohomology, which is studies de Rham complex. So this is a cochain complex. That's why the degrees are going up as you go from left to right. And so these are vector spaces and linear maps. And so Ci, so the ith step in this vector space sequence, is the space of differential I-forms on X. And these are given by sort of wedge products of basis vectors, if you've ever seen them in calculus or something like that. So the point is that there's a basis of these dx, wedge dy, wedge dz, these types of things. And it obeys certain rules about if you see two copies of dx and then you wedge them together, then you get 0. So this is called the alternating algebra of x. And the scalars here are the ring of smooth functions. So C0 is itself all smooth functions from x to the real line. And then C1 is like d of some such function. So it lives in the cotangent line and all of that. So if you want to describe this d thoroughly, so in local coordinates, it looks like this. So any element in Ci is going to be smooth map f, and then dx1 wedge, all of that. So that's sort of the basis element, and these get summed over all possible dx wedge stuff. And so the formula for the exterior derivative is you sum over the partial derivatives of f, and each time you have a partial derivative, you add a dxk. So I don't know if you can see my mouse. I hope you can. So that thing gets added, and the rest of this remains as it is. And so dxk was already there on the right. That part would give you 0, and then everything else would survive. Okay, so why am I talking about this? It's because in the 50s, Kuosai Chen had the idea to relate differential forms on x to the differential forms of this very scary looking loop space, omega x. So the question is, can you learn something about the cohomology of the loop space from the cohomology of x itself by exploiting these differential forms? And I should say that that the first thing in red at the top, the Durand complex, its cohomology agrees with the cohomology effect. So these differential forms learn something about the topology of the space on which they're defined. And so Chen's lovely idea, and this is absolutely it was groundbreaking at the time, is to take a whole collection of differential forms defined on X, put them through a machine, and get a single differential form defined on the loop space. And so you take omega 1, omega 2, omega 3, all the way up to omega k. These are differential forms on X. And then this operation gives you a single differential form. And the degree it lives in depends on the degrees of the differential forms you fed it via that formula. So if it's I1, I2, all the way up to Ik, you add them up, subtract the total number, and you get a differential form. This is a bit too general for our interests here. So let me sort of dial back a little. The case that will be of interest is when all of the i's are equal to 1. So what you get on the right side is a 0 form, because all of the i's are 1, so you add up k copies of 1, subtract k, so that's 0. So you get a 0 form in the loop space, which means it's just an ordinary function, because that's what C0 in the Durand complex was. And now we can get very specific. So you have a loop. Let's say I'm writing it as an image of 0, 1 to x, but gamma of 0 and gamma 1 are the same because it's a loop. So the dimension of x is 2, and the local coordinates are implicit. There's an x and a y as usual. Okay, so if you have omega 1 being dx and omega 2 being dy, the sort of two basis forms, then and you put them through as the two things into this Chen machine, then you get out the function that sends st to this integral. So you take a first derivative of the second one and the first derivative of the first one, multiply those two together, and integrate over what's basically a simplex. So I'll explain this in more detail later. I just wanted an example out there first. And Chen's theorem was that this image gives you a new sort of sub-Durand complex of the full Durand complex of omega x. So that sounds like you get at least some partial information about the cohomology omega x this way. And in fact, he went a little step further, which is if x was simply connected, which is to say if pi1 of x vanished, then this would be an isomorphism of the homology. So you'd see everything, all the interesting differential forms on the loop space would come from performing this operation to certain differential forms in the original space. Okay, so this looks like a sort of very deep abstract machine for learning things about loop spaces. Why would you ever care about it? Well, one thing you might be interested in are some nice, almost combinatorial properties coming out of this algebra. So what I mean by combinatorial is the notion of sort of permutation groups, finite permutation groups. So if you take the set of numbers from 1 to k plus L, then a k shuffle is a permutation that satisfies these two long strings of inequalities. Now, I never remember these inequalities. All I remember is this picture. So you have a deck of cards, split it in, there's k on one side, L on the other. And what you're allowed to do is shuffle them in any way you like. So the ordering on the left will get preserved, the ordering on the right will get preserved, but among them, there's no sort of rule deciding what goes first and what goes after. So that's what a KL shuffle is. There's K things whose order you preserve, there's L things whose order you preserve, and then you intersperse them any way you like. So that's a KL shuffle. And so one of Chen's lovely theorems was that if I take these K plus L differential forms, and I take the first K, perform the operation on them, take the last L, perform the operation on them, and wedge them together, which is really the only thing to do with the differential form, then I get up to signs, I get a sum of KL shuffles of having performed the operation of all KL, K plus L of them. Maybe okay, so this might also look weird. All I want you to remember from this, if you haven't seen this before, is that the higher order terms, the ones on the right, linear combinations of the higher order terms are non-linear combinations of the lower order terms. So you can take a K plus L term, and that is, so the linear combination of all K plus L terms looks like this non-linear wedge product of all K terms and then all of the L terms. This will come back to inform us. Okay, now maybe you don't care about loop spaces at all, and maybe all of this is terrible and boring for you. So let me say we're now moving out of loop space land into something more concrete, which is the study of differential equations. But keep these things like at least as much in mind as possible. Okay, so we're transitioning from topology to dynamical systems, and I'll tell you what's happening. We want to solve an ordinary differential equation, dx dt equals fx dt. So classical differential equation, you might see this in your undergraduate degree or something. And there's a sort of lovely iteration method for solving these. So you want to solve the one dx dt equals fxt. So you start with the constant function, and then there's the update rule up on the slide, c plus integrate of the previous iteration. So let me show you what it does in an example where we all know the answer. So, let's say we want to solve f of xt equals x. So dx dt equals x of t. We all know the answer to this, but let's come up with it together. So x0 is some constant, let's say 1. So what's the next iterate of this iteration scheme that we're trying to solve the system with? Well, it's 1 plus the integral from 0 to t of the previous iterate. So that just gives you 1 plus t. Okay, next, 1 plus the integral of the previous iterate. This is 1 plus integral of 1 plus t, which is t plus t squared over 2. If you keep doing this, so now you have a quadratic term. If you keep doing this, okay, so there's a third term. What's happening is you're summing up, you're finding the power series expansion for e to the x, which of course correctly solves the differential equation. So so this is sort of for the easiest types of differential equations. Now, if the differential equation is being controlled by a path, which means it has the form dy dt is f y of t dx of t, where y is a thing you want to solve for, and dx of t, that is some path. So there's a path that is changing the dx term as you go over time. So this is called a differential equation controlled by the path x. And f is usually a function that takes a vector and spits out a matrix of those dimensions. So it takes an n-dimensional vector and it produces an n by n matrix. Okay, so this is a differential equation controlled by the path, and we say we have a solution if it solves the corresponding integral equation. So y of t is the integral from 0 to t of f of y as dx of s. So in most of the applications, f is a nice linear map, but the paths are not even smooth. So there's no, the dx is just purely notational. You can integrate it, but you really cannot take any derivatives. So maybe the path is something like of bounded variation. So we can do more general things, but a bounded variation path is the one where this sort of derivative-like sum of x of ti plus 1 minus x of ti over any partition ti is finite. So let's work in the space of bounded variation path. So we assume that x is bounded variation. That's driving the equation. But we don't know anything about its derivative. In fact, in general, it won't have any derivatives anywhere. It'll be not differentiable. So let BV of Rn denote the paths of bounded variation in that dimensional space. So here's the basic idea, that we can use Picard iteration to solve these control differential equations whenever x is in bounded variation path and f is a linear map. Now, this is due to Terry Lyons, one of my colleagues here at Oxford, and this is from 1998. So I just want you to remember the Chen story started in 1950, and this is basically, it's almost 50 years after all of that, maybe slightly less. And it's also in a completely different universe. I mean, we're not dealing with topological spaces. We're not dealing with continuous functions. We're not dealing with group spaces. We're dealing with solving differential equations driven by rough paths. Okay, so the good news is we can take the Picard iteration scheme and use it for solving these more complicated classes of differential equations. So, so you have this f that was taking in an n-dimensional vector and spitting out an n by n matrix. To iterate, you want a square matrix. So, so what you do is there's a clever construction where you generate, instead of f, you generate a new matrix G. So it takes a vector of m dimensions and spits out an n by n matrix along this rule. And now we can start Picard iteration because we have an n by n matrix and you can sort of square and cube it and so on. So start with the initial guess. It's just a constant for all time. And then here's the first iteration. It's c plus the integral of your previous guess, which in this case is the identity plus the integral from 0 to t of the derivative of g composed with x. Okay. If you do this again, you start to see, okay, identity plus, the dg of x, and then products over the same thing as we were seeing before. If you do this in general, all of the terms you see will have this following form. You integrate from 0 less than t1, less than t2, all the way up to less than tk. That tk has to be less than the t. And then inside you have all these derivatives of g composed x. And these derivatives are, of course, because x itself is rough, these are all rough. So all we can do is integrate these things. We cannot take further derivatives. Okay. All I want you to remember is that these things, integral over 0 to t, 0 to s, dgx of s, dgx of u, looks almost exactly like the integrals we had in when dealing with the Chen theorem, which is to say that these are differential forms in some sense, and we are taking these partial integrations and getting something out of the loop space. Now, In the old setup, the space X that we wanted to study, or its loop space, was very, very exciting. Right, this is what we wanted to learn. It could be any exotic looking manifolds. Over here, the space X is very boring. It's just Rn. It's just Euclidean space. It's not got very exciting cohomology. We know what the cohomology is. What's changed here in the transition from all the red slides with topology to the blue sides of dynamical systems, what's really fundamentally changed here is that the spaces have become far less complicated and the maps have become far less smooth. So there's a trade-off here where the space becomes easy, but the maps are these bounded variation paths instead of the nice continuous ones we were looking at before. So that's the trade-off over 40 years of sort of evolution in this circle of ideas, where the space becomes really, really easy and the maps become really hard. Anyhow, so there's sort of now a discrete, not discrete, but dynamical systems version of Chen's construction, which is called the path signature. So here's what it does. It eats a single path, which is called gamma. And this is just a bounded variation, so it's not smooth or anything like that, despite what I've drawn. And it spits out a whole series of numbers. Or you can think of them as functions if you'd like. So how does it work? At the 0th stage, you just spit out 1, regardless of the input, so that's not so exciting. At the first stage, you spit out the integral from 0 to 1 of d gamma I of t. So remember, gamma is living in n-dimensional space, so gamma I is its ith component. So you do d gamma I and integrate that from 0 to 1 because it's a bounded variation path. This integral makes sense. And you get one of these numbers for every I, so you get n such numbers. Okay, so now I have a 1, I have n numbers coming from integrating every component of my path from 0 to 1. Easy, I hope. Okay, the next stage, you integrate from 0 to t and then 0, 1. So it's a simplex with 1 on one side and t, like this. It's half of the unit square. That's what you're integrating it on. And now you do all possible pairs, gamma I of t, gamma j of s, integrated on these simplices. Now, it's important that we're integrating on the half cube and not the full cube. If you're integrating on the cube, you'd have Fubini's theorem, and these things would, give you the same answer, whether you had I before j or j before I. But because you're integrating on the simplex, you genuinely have n squared terms here, because it doesn't commute when you switch the I and the j. So there's n squared numbers here, and similarly there'll be n cubed numbers, n to the 4th numbers, and all of that. So you're taking a single path and you're using its d gamma i's basically as the differential forms that you're feeding into the Chen integral machine, and now you get this huge array of numbers, which in each degree, so in degree d you get n to the d numbers. If you wanted to make all of this formal, if you wanted to do this in a principled way, then you're sort of forced to the following definition. So the signature of this path gamma is an element living in the tensor algebra of the n-dimensional Euclidean space Rn. And that's the definition of the tensor algebra. So it's a product of Rn tensored with itself m times as m goes all the way out to infinity. So the terms on the right-hand side with 2 are living in the level m equals 2. Then level m equals 3 is a larger tensor product, and all of that all the way down. And as said before, m indicates the level of the signature. And in practice, because eventually I do want to talk about data analysis and finite things, we sort of truncate so that m equals 5 or 6 or 8 or something, and then think of it as a sort of finite dimensional vector, because at the moment it's very, very and the mth level has n to the m components. We sort of computed that already. Okay. Because this is coming from integrals of differential forms as defined by Chen, even though it's in a new context, a lot of the old glorious properties are preserved. So let me give you a few examples. So if you have a path gamma, then the components of this signature are evaluations of Chen's iterated integral functions, where each omega I is a basis element, what we'd call dx's before. Okay. Another great property is if two of these paths, gamma and gamma prime, have the same signature, then they differ by basically a reparameterization. So their images are going to be the same, but the speed with which you are traversing those images might change. So they're up to how you have described the path. They're completely equivalent. So it's a very strong invariant of these bounded variation paths. It gives you the same sequence of numbers if and only if the paths are basically the same path up to this reparameterization. There's also a lovely homomorphism type property where the signature of the composite paths. So if you went back to the loop space, this is the product in the loop space. So gamma is a point in the loop space, delta is a point in the loop space, and then gamma star delta is you do gamma first and then delta. So if you took the composite path and you looked on the right-hand side, you would have a tensor product of the two images. So that's also very nice. So every how do you sort of get a handle on this very long list of numbers? So you take a multi-index I1 through Ik. Each I is living between 1 and n, and this gives you a component Si gamma, which must live in level K of the signature. And the shuffle product thing that we did with the cards here has a much simpler looking form. So Si gamma, Sj gamma, that product of these tensors is equal to the sum of K over K of Sk gamma, where K is ranging over all the Ij shuffles. So once again, the higher level components depend algebraically, not linearly, but algebraically on the lower dimensional components. And it's
Excuse me.
Yes.
I just have a quick question.
Sure.
So all these properties holds for paths in Rn, right?
Yes.
Yeah. So can you say something more general? I mean, paths in some maybe simply connected manifold.
It's not just simply connected. They work on any smooth. So bounded variation paths taking values in any on a manifold could make all of this work. This you can do it locally.
Okay.
But then you lose the sort of differential equation perspective if you were working in general. You have to drag a Riemannian metric along, and I didn't want to do that, but it works just fine in those cases. That's a great
thank
question.
you very much.
No worries. Okay, so it's particularly this last thing where the terms, the higher order terms that you want to truncate depend on the lower ones, which you will keep. So even if you truncate, you're not losing up to the sort of algebraic manipulation, that much information. So it's this property that has made the path signature such a useful map in machine learning. So what it does, it takes this complicated space of bounded variation paths and shoves it into the tensor algebra, which is also a very complicated space. But when you truncate, it takes all of these nonlinear properties, the higher order things, and yes, you have lost some information, but you can reconstruct some of it by doing nonlinear operations to the first few components of your path signature. So it's become a wonderful tool for analyzing this sort of time-varying data where paths arise naturally. So anytime you see sort of stock prices or heartbeats or something, things that are evolving time series of data, it's become an absolutely wonderful tool for doing feature maps. And I don't think I'll get into all of these, but things like handwriting of Chinese characters, like recognizing Chinese handwritten characters automatically. I think this is still the state of the art. Recognizing gaits, and, like sort of, distinguishing people from the way they walk. Financial data streams, like in Bloomberg terminals and things like that. So it's become a very wonderful and well-used tool for statistical inference when the data has the form of sort of one or more paths because then you can actually do these integrals. And okay, so there's more glorious properties that sort of help with the statistical inference aspect of things. So if you take the bounded variation paths and quotient by that tree-like equivalence relation, and take any compact subset of the space of paths, then the signature map, when restricted to that subspace, has three amazing properties for machine learning. The first one is that it's universal, which is to say that each continuous map, F, can be approximated to any degree of confidence you like. So any epsilon, you can get within epsilon of the continuous map by taking a linear functional and applying it to the signature, which is to say that your nonlinear map F defined on these compact subsets of path spaces can be recovered up to arbitrary precision from a very linear functional on the path signature space. So that's fantastic because it turns nonlinear problems into linear problems where we have tools of linear algebra, which are very highly developed to sort of solve those problems. So we can learn functions that are nonlinear using only linear information of acting on the signature. The second one is any probability measure on this. So you're sampling and getting paths, and you don't know what the method is that is generating these paths, right? You just have someone. You want to learn the probability measure among the possible paths. Why do you see the ones you see? So any Borel probability measure is recognized by its mean. So two different probability measures on K will have different expected values. This map sending a measure to its mean is injective, which means we can learn probability measures on path spaces, or at least compact subsets of path spaces, by just looking at the expected signature. Another very nice thing. And you can do this empirically, right? Just keep taking paths and then keep sampling them, computing the expected signature, and then ideally truncate it somewhere. And then you have a very good estimate of what the original probability measure looks like. Okay, and in terms of computation, if you're mapping to a Hilbert space, and this is probably why, going back to the excellent question I had about why we're working on vector spaces, the tensor product, the very nice thing about working on a vector space, like a Euclidean space or something like that, is that the tangent spaces are identified canonically. So at a point, the tangent spaces, at a point in Rn, the tangent space is Rn itself. On a manifold, this is no longer true, right? You have a tangent bundle that's varying from point to point. So this last property breaks if you're working with not a Hilbert space. But if V is a Hilbert space, then the map that takes this kappa map, which you take two paths and dot product their signatures with one another, is a kernel, which means, and in fact, this kernel can be estimated even when you don't know the individual signature. So this map, the signature map, is restricted to K is kernelizable, which helps when you want to sort of speed up computations. Okay. Hopefully, I know we went through a whirlwind of properties, first in topology, then in dynamical systems, then in statistical inference. I would like to now come back to topology, but in a completely different and far more practical context, because what we have been doing throughout this whole talk is starting very abstract and sort of becoming more and more sort of concrete and applied as things have moved on. The field of topology I'm actually in is called topological data analysis. And I want to give you sort of a two-slide summary of the whole enterprise. This started in the early 2000s, maybe late 1990s, just like some of the signature, the Lyons, Terry Lyons' work. So the idea is you start with a finite metric space. I've just drawn some points, and you can think about the sort of distances between them as generating a metric. If you want to study this, this is your data set. And you want to learn something about its shape. So what you do is you build a simplicial complex, a filtered simplicial complex. So think about that as a sort of graph on steroids where you allow not just edges, but triangles and tetrahedra and all of that. So And we're building it, we're making it bigger and bigger. So at scale level 0, you just get your data set back, nothing has happened. At the next scale level, you start connecting things that are within some distance r of each other. So that triangle is there because all 3 points are within some small distance r of each other. And as you make this r larger and larger, you add in more and more of these triangles and tetrahedrons. These are called simplices. And so you end up with a structure of a filtered simplicial complex whose vertices coincide with the original data set that you had. So we'll call this x epsilon, and epsilon is the scale that goes from 0 to some large number. Okay, now you compute homology. Hopefully you've seen some homology or cohomology in your life, but if you haven't, this is a method for taking things like simplicial complexes and producing sequences of vector spaces. So for example, the 0th homology counts how many connected components your space has. First homology is counting loops, and so on. So in each dimension D, you get a vector space, which is the Dth homology of the epsilon thickened filtered simplicial complex with coefficients in some field F. Now, the nice thing about homology is that it's not just spaces, you also get a map. So if delta is bigger than epsilon, there's a map from HD of x epsilon to HD of x delta. So you get like this sequence of vector spaces and linear maps. One of the sort of big revelations in the theory of persistent homology is that each one of these spaces of vector spaces and linear maps can be completely characterized by a combinatorial object called the barcode. So this is now indexed by dimension. So on the left, things were growing by scale value, and on the right, the scale value is now living inside the vector spaces, and it's just the homology, the dimension D and scale. The scale E has disappeared. It's a dimension D of homology that survived. And so that sequence of vector spaces can be completely characterized by a finite object called the barcode. So if you see in dimension 1, a bar going from epsilon 1 to epsilon 2, that means there was a cycle, a loop like the one that you can see over here that existed, that was born. The last edge came in at epsilon 1, and you filled in more and more and more. And at epsilon 2, some simplex came and sort of closed it off, and then it stopped being a loop. So that's when you get a bar. Anyhow, so you can completely characterize these R plus index vector spaces by these combinatorial invariants called the barcode. And what's nice about them is that they're combinatorial and finite, so you can feed them into a classifier like a neural network or something. And this whole pipeline, the hope is that it will give you some insight into your original metric space X. So that's topological data analysis in one slide. And all of the machinery used here was available sort of many decades ago. The reason it's picked up in the early 2000s was that we actually had computers to do all of this for us instead of doing it by hand. There's a new sort of theoretical aspect to this, which is called the stability theorem. I will not have time to talk about how it's proved or anything, but I want to give you a flavor of what makes this tick. So go back to your sort of finite metric space. Imagine it's just these points in the plane. And so in each dimension D, you get one of these barcode objects. So that was, chasing the arrows up until we feed it into the classifier. Now, let's imagine that the instrument with which you were measuring when you collected this data had some noise. So you don't really know that the points are where I've drawn them. Maybe they're just fuzzy, so you just know them up to these circles. So the real point could be anywhere in the circle. Well, the stability theorem says that no matter where the true points are in the circle, so if you take the noisy thing and you get this barcode, and then you realize that you had sort of an epsilon noise, what will happen is that the ends of these bars can only move by epsilon, either in or out. And so these very long bars, like the one at the top with the 2 circles, okay, I can move the endpoints, and the true answer is somewhere obtained by perturbing the endpoints of the bar by a little bit. The very small bars, though, the ones that are less than 2 epsilon, basically could get shrunk to nothing. And similarly, from nothing, you could get bars of length up to 2 epsilon, but no longer. So what this means is that sort of the longer bars are giving you the signal. They're the stuff that survives the noise, and the short bars, you cannot really trust them. So this is a new theorem from like 2004 or 5 or something. That's sort of new to this field of topological data analysis. I think it's a very nice result. It's a good combination of things that are sort of theoretical and have immediate application. So this gives the whole pipeline we saw up there robustness to this. Okay, so what does this have to do with the path signatures? Well, the trouble is that the distance between barcodes you get from moving the endpoints is not linear. So the space of barcodes is not a vector space in any nice way. And so there's lots of things you're used to doing when you're doing statistics, like, oh, I have 2 samples, I'll take the average, which you cannot do. There's no average of 2 barcodes. There's no good way to sort of do any statistics with them. So the typical thing, and if you've seen stuff like word2vec and all of that, when you have unstructured data and you want to do statistical inference, one of the most standard things is to first map it in a nice way to a vector space and then do all of the analysis in the vector space. So there has now been sort of, for the last 10, 11 years, there's been an industry of people taking persistent, this information, these barcodes are now also called persistence diagrams, and shoving them into vector spaces in sort of increasingly clever ways. So the oldest paper I know of is this one by Bubenik on using something called the persistence landscape. That's one way of embedding. And then there's a slice of Wasserstein kernel, persistence images, kernel method via embedding and weight factor. So you see, like, they're just all of these methods, and all they're doing is taking this combinatorial information about the beginning and end points of various bars and putting it in vector spaces. So what these path signatures do for us is that they allow us to create another one of these feature maps that has very, very nice properties, in some sense, like wonderful properties. If you want to do machine learning from persistence diagrams, that last arrow in the chain of topological data analysis pipeline. So here's the idea. It's just 2 steps. So you start with your given barcode that has come as an output of one of these processes. You create a path from that barcode. There's lots of ways of doing it. I'll show you a few here. And once you have that path, you map it to the tensor algebra and via the signature map. So these the IOTAs are called persistence path embeddings. So they take persistent homology information and give you paths. And S is the standard signature map that I have been talking about for much of the lecture. Okay, so the first example of these path embeddings comes from Bubenik's landscape function, which I just mentioned. So you take the bars, so you take the birth and the death, think of them as points in the XY plane. So imagine you had 3 bars, and then you get these 3 birth death points in the XY plane. Draw, these straight lines to the diagonal, down and to the right, tilt your head, and then you get the space on the right. This sort of landscape is what it's called. It looks like some nice mountain scenery is happening. So these are paths. So automatically they can be, they're already paths, so that's great. And it turns out that paths that if you take antiderivatives of this path, so partial integrals of these paths, they're stable with respect to perturbations of the original barcode. These are not so easy to compute because extracting the landscape is not so bad, but the signatures of these integrated landscapes are difficult to compute because they're no longer piecewise linear and they get piecewise parabolic. There's no nice software package, for instance. There's 2 sort of simpler embeddings. The first one is, so in each dimension, you let beta d of t be the number of bars that contain the number t. So the number of intervals that contain the number t. And then, so sending t to that number gives piecewise constant curves in Rm, where m is the largest dimension. This is not stable in the previous sense, but it's computable and very, very useful. And here is the Euler embedding, which you compute sort of what's called the Euler characteristic by taking the alternating sum of the previous number. So it just gives you a single path. What's nice about this is you don't have to compute any homology. You can just take alternating counts of the simplices. And they're both unstable. A sort of new one that we propose is called the envelope embedding. Take all of the bars that you get, arrange them in descending order of length, and then join all the deaths and all the births into two separate curves. So the blue one is the birth curve, the red one is the death curve here. And the longer bars appear before the shorter ones. Okay, so we compared two sort of various existing techniques for doing this sort of machine learning for persistence diagrams. Above the line, the KSW is called the slice Wasserstein kernel, and VPI is the persistence images maps. So these were two of the papers that I showed you that have done feature maps. And you will notice that we only lost the best classification result in one of the three sort of data sets that we'd seen. It was sort of orbits of a dynamical system. And so we were I was very sad to see this. But if you go to the paper, the persistence images paper where this is done, I think they obtained like an 83% accuracy. So what had happened was we used a better classifier on their results, and then their results improved a lot. But I mean, I don't think 98.8 is a terrible thing. Okay, so that's all I have. If you liked any of the material, you saw like the last bit about the merging of TDA and the topological data analysis and path signatures. Here's the paper. It appeared in the Transactions of Pattern Analysis and Machine Intelligence a few years ago. It's called Persistence Paths and Signature Features in Topological Data Analysis. So this is the machine learning from path signatures meets topological data analysis paper. Far more recently, we've tried to recreate some of these miracles for things that are not paths. So functions from, say, the square into some vector space or into some manifold. This already for d equal to 2 is much harder than the path case. And so this is our paper with Chad Giusti, Derek Lee, and Harold Oberhauser. And I guess the thing I want to end with is if you like the topology or the differential equation or the data analysis stuff, here are some references that might be helpful. That's all I have. Thank you so much for your attention. I'll take any questions.
Thank you, Vidit. I must say that this is the most elaborative and descriptive talk we ever had in this John Conway Spirit Examiner series. You try to encapsulate too many things in a very, very skillful and very elaborative way. I really appreciate it. And many things are new for many of us, including me. So any questions from the audience side? Yeah, please, Suzanne, go ahead.
Okay, so hello everyone. Thank you so much, Professor Vidit, for demonstrating such a nice way of vectorization of barcodes. You mentioned in the slide that landscape embeddings are stable, right?
Iterated landscapes embedding.
Okay, so iterated landscape embeddings are
As integrated, not iterated, integrated. So you take the function, the triangle functions, and then you integrate them to get parabolas, and then that parabola thing is stable.
Okay, so my question is, what metric are you considering to define their stability?
Yeah, this is great. So on the left side, so this is an assignment from barcodes to paths of bounded variation. So on the right hand side, once you get these paths, it's the one variation metric on bounded variation paths. I can define it if you like, but you can look it up easily. It's one variation metric. And on the left side, you have these barcodes. It's called the bottleneck distance. So these are the sort of natural notions of distance on the domain. It's exactly what you want to come up with if you thought about it for a bit. But yeah, the terms to look up are bottleneck metric on barcodes and one variation metric on paths.
Right. So is it natural to consider L infinity metrics or a barcode in one-dimensional setting in one-dimensional persistence.
Is it natural to consider L infinity metrics? You mean on the barcodes themselves, or on the feature maps?
On the barcodes.
Yeah, so the stability result, the bottleneck stability is very much an L infinity type. It measures the maximum you have to sort of deform one bar into the other. It doesn't take a sum over all of them like an LP type distance, like an L1 distance. So it is natural in that sense, but it's also so. The metric is sort of what you need it for is the big question about before you decide. So say you want to distinguish a circle from a noisy circle, right? That's like points on the exactly circle versus points in the noisy circle. In terms of bottleneck distance, the two persistence diagrams will not be very different. Because if you have a very small amount of noise, if you want to distinguish two noisy circles where one noise is of one type and the other noise of the other type, all the signal is living in the really tiny bars. Because the big structure is the same for both of them, right? So they'll both give you like this prominent bar from beginning to end that gives you the circle class, and then like just a bunch of noise. And if you really care about that bunch of noise, and you don't want your feature map to be stable because you don't want to ignore it, all of the stuff you care about lives in the little finicky details that you would otherwise ignore for stability reasons.
Okay, thanks. Okay, I get it. Thanks. Okay, so my next question is, can we apply this machinery? I mean, can we apply any of these embeddings to some higher dimensional barcodes or higher dimensional persistence module? Can we do that?
Higher dimensional barcodes meaning what?
From two-dimensional multi-parameter setting.
So in the multi-parameter setting, you don't have. So you lose two things. One is you don't have barcodes in the traditional sense. You don't get these birth depth.
Yeah, in the traditional sense, we don't have any barcodes, but there are several invariants exist which can serve as surrogate for these barcodes in the multi-parameter setting.
So my I did think about this a little. So there, I have two answers to that. The first one is if you're able to take the data of your multi-parameter persistence module or your some invariant, like a rank invariant or whatever, are able to reasonably compute and turn that into paths in a sort of intelligent way, then yes, right? Because the minute you have a path, you can compute the signature, and that's it. That's done. The other answer would be that you probably want to look at this paper where we handle things that live on a grid. And create something like a path signature out of these. So you probably want a higher dimensional version of the path signature, which is called a mapping space signature. No promises that any of this is computable. We're still in the very early stages of this out.
Okay, thank you so much.
You're welcome.
Thank you. Are there any other questions from the audience? Okay. Okay, Vidit, I must say that this time we got very diverse audience, and lot of people keep on coming and attending the talk, and thank you very much for
You're most
accepting.
welcome.
Yeah,
thank you for having me.
Yeah, and I hope because there are few PhD students and some of our faculty members started working in this particular direction, and definitely this direction is quite new, and people are trying to understand it, and a very little community is familiar with the technicalities, evolving technicalities of this particular area. And I must say that this talk will entice many people, including myself, to explore further. So one very new question from because I'm not working in this particular direction, but I really want to know whether if okay, when we have a data, so what kind of information, okay, I'm thinking from a mathematical perspective, what kind of information, the Betti numbers, the topological invariants are giving in the sense of the data analysis. You mean in the decision making or something like that? Or this study? Let me
Sorry,
just
I
mute
didn't.
them.
I think somebody is muted. But well, so the lower dimensional ones are always the easy ones to interpret, right? So 0 dimensions is just about as you thicken your data points,
Yeah.
what pieces, like how many pieces do you have as a function of that scaling? So the beginning, you have as many pieces as you have data points, and then at the end, you just have one giant blob. If you grow your scale, right? So this looks exactly like the single linkage clustering. So it gives you whatever you understand from single linkage clustering. Like it's a
Okay.
And now in even dimension 1, it's sort of difficult, right? So you see sort of a tunnel or something like that,
Yeah.
and then it gets filled in. But if it gets filled in at the edges, then it'll create 2 cavities. If it gets filled in like if it gets pinched in 3 different places, you get 2 cavities. So there are sort of geometric interpretations for the Betty numbers. But what's I think more common these days is there's a very simple test, right? So you ask, do the Betty numbers or do the persistent homology groups tell me anything interesting? And let's say you have a classification point. You want to tell the difference between apples and oranges, but you don't know that this one's an apple and that's an orange. So 2 different data sets. So what do people do? They use some machine learning to tell them apart. They get 85% accuracy, right? They can tell these 2 apart. And then you add something to your feature vector coming from persistence or Betty numbers. Now, there's a chance that nothing improves. There's a chance things get worse. And then there's a chance that you get 92%. And if you get 92%, you say, well, I can measure the improvement. And then nobody asks you questions because anyway, the classifiers we work with these days, they don't tell us why anymore, right? That people have very happily given that up for a more predictably sort of accurate classifier. So if you're going to use deep learning or something like that anyway, then asking what does this say about my data? I mean, people have sacrificed that a million years ago. Or 10 years ago, but it feels like a million years ago. So that's one answer. But for the low dimension ones, you can in general, do something. So the closest analog would be imagine single linkage clustering type things, but for holes instead of components. That's the only slogan I have, but I don't know if that helps you.
Yeah, I think that's a fair answer to the one who knows the mathematical side and really thinking about what interests the persons who are working in the data science or what are the meanings of those computation of first level homology, second level homology for a data scientist. So anyways, thank you, Vidit. Thank you very much for your presence in the John Conway Spirited Seminar Series, and it was a wonderful talk.
Question?
Oh, okay. Please, Zaira, go ahead.
Instability, you considered the bottleneck distance. So I just wanted to know if there's some relation with the interleaving distance, because that's more general.
Yes. So the interleaving distance is defined on persistence modules, like just the sequences of vector spaces and linear maps, whereas the bottleneck distance is defined on the sort of bar codes that you get at the end. And there's a theorem called the isometry theorem that says if the persistence modules are tame, which means that none of the vector spaces have dimension that goes to infinity. So all the vector spaces are finite dimensional, and there's only finitely many points where they change rank, where they change dimension. So it's a technical condition called tameness. So for tame persistence modules, the interleaving distance and the bottleneck distance are the same. It's an isometry. So maybe I should say that I've been teaching this TDA course at Oxford for a few years now. You go to my website, there's a set of lecture notes, and hopefully I wish I'd written them down now. But so on my website, there's a computational algebraic topology lecture course, and there's lecture notes, or on my Twitter, I think it's the pin tweet or something, and also videos. So I do describe this isometry theorem relating the interleaving distance to the bottleneck distance in chapter 6 of those notes.
Okay, thank you.
Perfect. Still, are there any questions from the audience?
Yeah, this is great. The more questions, the better.
Yeah. Okay. Okay. Junaid, any concluding remark from your side? Yeah.
Excuse me, from my side.
Yeah.
Yeah, okay. So it was a wonderful talk. I really enjoyed. You know, I don't know much about these data science, but of course, the mathematical side was very interesting for me. Thank you very much
Thank you.
for this nice talk.
Thank you. Thank you.
Just a question, maybe.
Okay.
So 2 years ago, I found an article which was relating knot theory with this machine learning. So can you say something about it? I mean, do they follow the same route? For example, the
Knot
loop
theory and
space.
machine learning.
Yeah, yeah.
No, I don't know anything about that. Sorry, it's not my area. I don't know.
Okay. Thank you very much for this nice talk.
No worries.
Okay.
All right.
Okay.
See you all.
So
Thanks
see
for
you
coming.
all. Thank you, Vidit. Thank you, everyone. Bye-bye. Take care.
Bye.